Hello and welcome everyone. Today we are diving into one of the most advanced tools for electromagnetic simulation, Ansys Maxwell. Whether you are designing electric motors, transformer, or any system involving electromagnetic fields, Maxwell can be a very powerful tool to simulate that. So in this session, we'll explore the process of generalized finite element analysis. We'll provide an overview of Ansys Maxwell, and we'll take a closer look at its solvers that simulate and optimize electromagnetic and different type of electromagnetic devices. So by the end of this introduction, you'll have a clear understanding of how Ansys Maxwell works and which solution type we need to use according to our simulation requirement to achieve a greater accuracy and efficiency. So we'll go through a basic idea of what are all we're going to cover in the session. So we'll discuss first the introduction of finite element analysis. Then we'll deep dive into introduction of Ansys Maxwell. And then we'll discuss what are all the solvers we have in the Maxwell, and we'll end with the application where we can use the Ansys Maxwell. So introducing a finite element analysis, first step is to have a geometry. So we will be requiring a concept of our geometry that we are interested in simulating. Then once we have that concept geometry, we need to assign appropriate material properties to that. For example, if we want to simulate motors, which we'll be doing in later sessions. So let's say I want to simulate a motor, then I know that in a motor there will be a different components such as a stator, rotor. If we have a permanent magnet motors, then there will be a permanent magnets and windings. So each of those component will be comprised of a different materials. So in order to get a proper results of our simulation, we need to make sure that we are assigning a appropriate material properties to each of the component. So once we do that, we'll move back to excitations. So excitation is nothing but kind of an applying the loading conditions, like how my winding is distributed, where how many turns I have in each of the phases, how the progression of windings are there, what current those windings will be carrying, what type of a waveform they will be having, and all those things. Then once we are done with the excitations, then comes the boundary conditions. So in electromagnetic, boundary conditions play a very critical role. It helps in determining how electromagnetic fields behave at the interfaces between two different materials or multiple materials. So these conditions, help us to ensure that Maxwell's equation, which actually govern the electromagnetic behavior, are satisfied within various scenarios. So electromagnetic fields, if we talk about the boundary conditions, so electromagnetic fields must satisfy certain continuity conditions across the boundaries. For example, a tangential component of the electric field and the normal component of the magnetic field must be continuous. So those conditions are ensures that the accurate magnetic field distribution. So boundary conditions reduces the computational complexity by defining the problem domain limits and minimizing the need to model a vast surrounding space and all. So this way, boundary conditions play a very vital role in how accurate and how fast we will get our simulation results and all. Then comes the meshing. So meshing is nothing but dividing a whole solution domain or our complete geometry into smaller finite elements. Now the finite element can be different for a different software. It can be a triangular, it can be rectangular, it can be some other shape which is considered as a finite element. Okay, Once we are done with that meshing, then we'll apply the analysis setup, like how my machine wants to solve, how long I want to solve it, and all those things. And once all the numerical analysis and all the solutions process is completed, the last thing that stays is the post processing, or we call it as a result analysis, where we plot the graphs, we see the fields, we evaluate a different quantities and all those things for our analysis purpose, and we see that how the machine, or the model which we are interested in, how it is performing in terms of electromagnetic behavior. So introducing a basic idea of Ansys Maxwell. So Ansys Maxwell is a finite element method based low frequency electromagnetic solver, and to solve those low frequency electromagnetic problems, it uses the Maxwell's equation, which we have presented over here. You can see all four fundamental equation in terms of differential form. So now the question comes that how do we know that which frequency is to be considered as a low frequency? So if the largest dimension of the model is less than 1/10 of the wavelength, then that frequency of operation is considered as a low frequency. And in those cases, Maxwell will be a appropriate simulation tool to go with. Now, how do we calculate the wavelength? So wavelength is nothing but the division of speed of light by the operating frequency, or say the maximum operating frequency that we can consider it. So this gives a basic overview of Ansys Maxwell. We will be going in detail as we start on further simulation procedures, where we simulate different applications, and then we will discuss what is important and how Maxwell handles a certain type of quantities in those cases. So discussing about the solvers in a Maxwell. So Maxwell is characterized broadly in a two different major solver types, one being the magnetic solver and the other one being the electric solver. So in a magnetic solver, as the name suggests itself, we will be studying about all in terms of a magnetic effect. So whenever we are interested in the quantities that is related to the magnetic field, we'll have to go with the magnetic solver, such as the transformer or the motor operations and all, or how two different let's say magnets are exerting forces on that each other. Those type of simulation we can do with the magnetic solver. Then similar to that, when we are interested in a electric field simulation, then we will be doing with those effect and simulation in case of an electric solver. So magnetic solvers are defined with the three subcategories. One is the magnetostatic, the other one is the eddy current, and the third one is the transient. Similar to that, electric solvers are characterized in four different types. One, electrostatic, DC conduction, AC conduction, and transient. So let's have a look at each of the cases and what that does individually. So looking at the first of magnetic solvers, so first is a magnetostatic. So magnetostatic solver solves the magnetic field that is caused by a DC current and say a permanent magnets, and it can solve both linear as well as a non-linear material. Now the question that comes is that when we should be using the magnetostatic solver. So if you have a quantity that is of your interest which is time invariant, for example the magnetic field that is caused by the DC current and permanent magnets, they will not be changing with respect to time. So in those conditions we can use the magnetostatic solvers. The quantities for which the magnetostatic field simulator solves are the magnetic field H and the current distribution J. The magnetic flux density B will be automatically calculated from the H field. The derived quantities which we can further evaluate from the solvers are forces, torque, energies, inductances and all. Then comes the eddy current solver. So eddy current solver solves the magnetic field which are varying sinusoidally, and it solves in a frequency domain. So here it solves both linear and non-linear material, okay, and it can also consider the displacement currents, okay. So induced fields such as the skin and current proximity effect, those things are also considered here. So if we are interested in, let's say, power transformer simulations, okay, and we want to see how the losses are distributed with the sinusoidally varying frequencies, then we can use this eddy current solvers. Then comes the transient magnetic. So transient magnetic solves the field those are caused by the time varying, or let's say the moving sources, and even the permanent magnets. Here it can solve both linear as well as non-linear material, and induced fields such as the skin and current the proximity effects and all those things are also considered here. Now transient magnetic is widely used for the motor simulations and all those things, where we have a movement of the rotor also involved, and the current is also time varying. And also it is not sometimes fixed that we have always the sinusoidal current. It can be PWM based, it can be somewhat distorted, or let's say we have some harmonic included into our waveform and all. So that type of waveform also transient can simulate. So moving to electrical solvers. So here electrostatic solvers is similar to that of the magnetostatic, but here it solves the static electric fields, but here it only solves in the linear materials. It cannot handle the non-linear material properties. Then the DC conduction. So DC conduction will solve for the voltage, electric field and the current density from the applied potential. So it can also solve the electric field distribution in an insulator. So here DC conduction field simulator that helps in computing the steady state 2D or 3D electric field in a conductors due to current excitation or the applied for potential. Now the quantity for which the electric conduction field simulation, or the, let's say, DC conduction field simulator solve is the electric potential, the electric field and the current density. The current density are automatically calculated from the potential. Now as an additional option, perfect insulator, that is a non-conducting region which is say surrounded by the conductor, can also be added to the simulation domain, that will allow to calculate the electric field everywhere including the insulator as well, okay. So now about the AC conduction. So AC conduction simulator, or let's say the solver, it helps in solving the sinusoidally time varying electric fields, but it solves in a frequency domain. AC conduction field solvers allows you to analyze both conduction and displacement currents due to time varying electric fields in the conductor, and perfect also a lossy dielectric, okay. User can analyze current distribution, electric field distribution and potential differences, and also the CG parameters. For instance, the admittance matrix associated with the structure can be computed using AC conduction field solver. So Here is a basic overview of all the solvers and when to use the which one. So now about the application. So Maxwell can widely used in all of those application which we have mentioned here. So here you can simulate electrical machine and drives in order to simulate motor performances and how they can behave it in, when we are coupling with the drives, where we don't have a conventional type of a supply, but we have it our own different type of a supply, be it a BLDC and PMSM type of a machines and all. Then we can simulate both power and electronic transformers as well. We can use to simulate the wireless charging or wireless power transfer, magnetic latching, power electronics such as a cable and bus bar can also be simulated. We can use with the actuators, magnetic sensors, as well as the induction heating. So this was the basic overview of the Maxwell and where we can simulate those kind of conditions using the Maxwell. So with that, I will keep it over here, and thank you for watching, and let me know your thoughts in the comment section. If you have any queries related to Maxwell solvers and all, we'll reply in the comment. Thank you.